So any questions on the Blackboard side? Like I said, the college added all these buttons down here, which basically are from the college's homepage. But I guess they decided they didn't want you to try to go two different places to do different things. So what we're going to do is we're going to start off with an introduction, and we looked at this a little bit the other class, but we'll go back and pick up on this. Because I think the recording got wiped out anyway. So we talked about the definition of what a sensor is, right? What's a sensor? Now there's a little difference between a transducer and a sensor, but most people use these, and you can look up the definition. I think I've got, you can look up the definition of those, but most people consider these two to be exactly the same thing. So some people call them transducers, which is a device that takes something and changes it into another form, which is what a sensor is. So a sensor is a transducer. A transducer doesn't have to be a sensor. Makes sense? It's just like a Ford is a car, but a car don't have to be a Ford. So a transducer is something that takes it in one form and changes it into another. So it might take physical and changes it into chemical. Well, that's not a sensor, that's a transducer. You understand that? So something that takes it in one form and changes it to another form is a transducer. A sensor is a transducer that takes physical stimulus and changes it into what? Electrical. So that's what we're saying. It's like a Ford is a car, so a sensor is a transducer, but a car don't have to be a Ford. Y'all understand that? That's the best way I can put it. So a sensor is a device that takes a physical stimulus and transfers it into or changes it into its what? Electrical equipment. Everybody understand that? So that's where that little touch will work. Now what we pick up is something we call a transfer function. So we're going to have some type of physical stimulus. So let's talk about what's some of the things that we might want to sense. Okay. So presence, weight, distance, yeah, we can just go on. Temperature, yeah, material, color. Did I miss one yet? Yeah, gases. Yeah, fluid. Level, which is basically distance. So usually some of the sensors we use to sense distance can also be used to sense level. Oh yeah, motion. Pressure. Well, if I want to sense pressure, I want also source. I don't understand the difference between a pressure and source. I mean a force. No, they're not.
Pressure would be like air pressure in your tire. Force.
We cannot have a force without a pressure. Right? What's that? We have to have force to have motion. To have force, we have to have pressure.
If you're going to air that tire up, you got to have that air.
But it generates a force.
Pressure in the tank.
Well, yeah, but we're taking that pressure to generate force. So my car weighs 2,000 pounds. It don't weigh 30 psi. Right? You understand that? So pressure is something that creates a force. So force, which is something that will cause a device to tend to or change directions, is equal to area times pressure. So we can't have force unless we have a what? Pressure. So pressure is a push, right? You understand? Or it's a difference in potential. And then if we got pressure, then we can have a force, but we're going to have to push that against a what? An area. So pressure is the actual push that causes the direction change. But the pressure's got to push against something. If we don't push against something, then we don't have what? Force. So we have force sensors, we have pressure sensors. They're two different things, right? You understand? So pressure might be like in here over using the U.S. customary, our pressures are in PSI, pounds per square inch, right? Okay. Then force is in pounds or tons of the units that we have in our U.S. customary. So measure force, measure pressure. Any more? So we got weight. Now these could be the same. A weight and a force are the same, right? You understand that? So when I get on my scales, it weighs me in pounds. And what it's measuring? It's measuring a what? A force. So those are the same. Any more?
Well, I figured foundation for the building. You take the weight of the material.
Okay, so that would measure weight or force, yeah.
Light and color.
Well, not necessarily. Detection of light and detection of color is two different things. So we got how many different sensors do we have in our eyes? In our eyes, we got one that just senses light. It's a grayscale sensor. It don't sense color. It just senses light. Grayscale. That's our black sensor. And then we got rods and cones. I forgot which one of them is nothing but a light sensor. The other one is a color sensor. And then when we combine black with these three different colors, then we can get an infinite number of color combinations. What else do we need to detect? I mean, we could go on, but there's one that's very important. Speed. Yeah, speed. How fast? We got distance up here. Speed, right? Need to be able to sense speed. I mean, you're driving your car and you gauge that, and you gauge your cruise control. It's got to have some type of sensor that senses the speed that you're going to know what speed to maintain, right? Y'all understand? And also another one that nobody brought up. Position. I mean, we're gonna have to sense position. We're constantly trying to know when things are at certain places, right? You understand? So these are just a few, but what the transfer function is going to take that position and convert it into an electrical equivalent. It's going to take that motion and convert it into electrical equivalent. It's going to be a math formula. And basically it's pretty easy. It's just the basic gain formula. It's going to be out over E. And this deals with the transfer function. Doesn't deal with digital signals. It deals primarily with analog signals. So let's say we're going to get out. What would I put in on my pressure? What would I get out? What electrical quantities do we normally use? Say the electrical equivalent. Voltage is the most popular, followed by current. It's hard for me to send resistance. You understand that? Even though we have a lot of sensors that sense by changing their resistance, normally we apply a voltage to that so we can either get a current or we can get a voltage out of the thing. So the two primary methods we use to send information, even digital information, we usually use the voltage or we use the current. It's very hard to see resistance. I don't know of any sensor that sees resistance. So if I was going to bring in a pressure, and we'll just do this, we would come up here and say, okay, normally what we do is we take our maximum output voltage, let's say 10 volts, and then we then we divide it by our maximum pressure. So let's say the maximum my pressure sensor would put out would be 100 psi. Well, my transfer function would be equal to what? So I take 10, right, you understand? And then what would I come up with? 10 divided by 100, what's that? Okay, 100 milli. So that's going to be 100 millivolts per psi. So now I've got a transfer function, right? You understand? So if I put 10 psi, then my sensor would give me 1 volt. We call this a transfer function. So the transfer function, we take what we're getting out, so it's always going to either be what? It's going to be a current or it's going to be a voltage, and we're going to divide that by a set quantity. It don't have to be the maximum. Normally that's what we use. We use the maximum output of my sensor divided by the maximum pressure or the maximum speed or the maximum force or the maximum amount of light or whatever would go on the bottom. And this will give me so many millivolts per pound or so many millivolts per lumen or so many millivolts per psi or so many millivolts per this. Now once I've got my transfer function, then I can calculate what to expect on anywhere between the minimum range of my analog sensor and my maximum range. And we call that the transfer rate. So it's the ratio between the stimulus and the electrical equivalent. But it's always what? What we get out divided by what? What we put in. And then once we know that, then we can calibrate it. Now it means something. Now if I get 5 volts out of my sensor, it means something, right? You understand? So if I put 5 volts out of my sensor, it means I was getting 50 psi. My sensor was measuring 50 psi, and we refer to this as the transfer function. Everybody okay there? Pretty neat. And these are for analog sensors. And of course, we talked about the 5 basic human senses the other day, but we have a lot more senses than the 5 senses that are listed here. And what did we come up with? We came up with a lot of the other class. These are just a few. If you research human sensors, these are some things that we have the ability to sense that a lot of people, I mean, you'll go up there and you'll say, people, what are our 5 senses? And you say, what are our senses? And just about everybody's going to say, well, yeah, they're going to say touch, smell. They're going to say these guys. These are the 5 basic senses. And, and how they came up with it, I have no idea. When we come up here, we know that we can sense all this stuff. We have the ability to sense. You know, this was pretty interesting, just to know where you're at, right? Equilibrium and all kinds of stuff. So analog versus digital. So this is a good example. So analog, what is analog? It is something that continuously varies over a range. It's always going to be over a range, right? So when I watch the weather at night, they give me the low and they give me the high. Well, that would be the range that the temperature would vary between the low and the high. And how many combinations of temperature does it vary in? An infinite number. We have no idea. We cannot calculate. Now we don't get into milli degrees, and we have to give up somewhere, like seconds. How much time is there between seconds? An infinite amount of time, right? You understand? If you had the ability, you keep dividing that and dividing it and dividing it, you could divide it forever, right? You understand? So we don't understand analog. Analog gives us the ability. So anybody that tells you that digital is more accurate than analog, they have no idea what analog is. In analog, I can represent infinity. I cannot represent infinity with digital. I'm going to have to give up sooner or later. Right? It's just that I cannot represent infinity with a number. So like pi. Pi is an infinite number. Pi goes on, they don't have no idea how long pi goes. So we give up on it, right? You understand? We say 3.14, we say 3.15, there's a little guy on one of these little old tiny kids that had memorized pi to 100 decimal points. Now they've calculated it out to over 1 billion points right now, and it still has not repeated. It's an unreal number. It never starts falling into a repeating pattern. So we don't understand analog. The problem is analog is continuous varying physical quantity. Usually we're going to represent it with a watt. Voltage or a current. Infinite number of values is more accurate, requires less bandwidth and low cost. The big problem we have is that it's susceptible to electromagnetic interference. It's almost impossible to maintain it over long distance. Because if I generate a current, if I generate a voltage, I've got to cause something to move. If I have a current, I got a resistance. If I've got a wire, I'm sending that through. Every wire has resistance. If I send a current through a wire, we have a voltage. We have ground differentials. We think of ground as 0 volts, but it's 0 volts on where you're at, right? You understand? So if I've got a building that's 1,000 feet long and I've only got one ground in my building, I guarantee you could go to the electrical outlets on one side of your building, and if you could stretch your meter long enough over to the other side of the building, there would be a difference in potential between the two grounds. So a ground potential is almost a 0 volt potential is almost impossible to maintain over distance. So I might be transmitting 5 volts. But I lose 1 volt in my transmission. Well, my other guy's only going to see 4 volts, right? You understand? So over here, 5 volts means something. Over there, I'm at 4 volts now. So analog, we have a big problem with transmitted over distance. We can't store it. How are we going to store analog? I mean, if I could charge a battery up to a certain voltage, but as soon as I take that voltage off, what does the battery instantly start doing? It starts discharging itself, right? You understand? So analog is almost impossible to store for later use. So usually when we bring in analog, we're going to have to use it what? Immediately. Yeah, we can't store it and use it later. Hard to process by computers. Computers are not analog devices. They are digital devices. All they understand is ones and zeros. And we got to represent that ones and zeros with an electrical quantity. What's the most predominant method of representing digital? Yeah, but we got to represent it with something. So if I'm going to bring it into a computer, that computer's got to represent that digital information with something electrical, right? You understand? And what's the most predominant method of representing ones and zeros? Voltage, yeah. We either have a voltage there or we don't have a voltage there. So a certain voltage would be considered a digital 1, and then we usually use 0 to represent digital 0. But the problem is that we can get by with having a range of voltages. So computers want ones and zeros. It's hard to interpret. So if we don't understand that transfer function, if I don't know what I'm measuring and I measure an analog output and it's giving me 3 volts, if I don't know the transfer function, it means what? It means nothing. Digital physical quantities vary in discrete steps. We have binary weighted numbers, and then we have just binary, single bit. So in binary, it's made up a bunch of ones and zeros. And this number has a weight. It's a number, and number has a weight to it, right? You understand? But what we don't understand, some of y'all might understand that. How's this thing set off? What weights does it use? Well, it uses weights of 2, powers of 2. And what's nice about a power of 2? So this guy here holds a weight of 2 raised to the 0. This guy right here holds a weight of what? to the first, this would be what? To the second, to the third, to the fourth, to the fifth, to the sixth, and it would go up a line. But that means nothing to me. Why is that? Well, most people don't understand twos, right? They don't understand powers of twos. So for me to understand the weight, what number system do we understand most? Yeah, decimal. Which we refer to as a base 10. And why is it called base 10? Well, most people don't understand that either. They don't teach this in school either. Yeah, so this holds the weight of the base, and that's why they call it base 10, because the base of an exponent is the number you raise to some power. So binary is a base 2, so it's going to use 2 raised to some power. Decimal is base 10, so it's going to use 10 raised to some power, right? You understand? So what would this be? And this would be what? 10 to the second, 10 to the third. And when we get on this side, what does this go to? Yeah, this moves to negative, -1, 10 to the -2. Now, I know these, and what we learn in elementary school is we learn the way, we learn the powers of tens, and they don't tell us it's the powers of 10. So any number raised to the 0 power is what? 1. Any number raised to the 0 power is 1. You can get it out of your calculator, and you can take 1 billion raised to the 0 power and look up and say what? 1. So any number raised, so we learned it as units. But this would be ones. This would be tens, because 10 raised to the first is 10, right? Any number raised to the first power is itself. So we learned this as 10. 10 squared is 100, so that's what we learned it as in school. We learned it as hundreds, right? This is 10 to the third. We learned that as thousands. 10 to the fourth is 10,000s. So that's the way we teach it in school. They don't tell you why it's called base 10. So base 2, we use 2 raised to some power. 2 to the 0. If I came up and put the binary point right here, what would be right there? 2 to the -1. What would that be? 2 to the -2, 2 to the -3. But it still makes no sense to me. A base 8. 8 to the 0, 8 to the first, 8 to the 8. Base 16. 16 to the 0, 16 to the first, 16. But if I don't understand 16 to the 0, I know it's 1. 16 to the first, I know it's 16. Then I get 16 squared, and now I'm gone, right? How many people know it's 256? Right? You understand that? So what I need to do is I need to get this binary number into a decimal equivalent, because decimal makes sense to me. We're not going to do that whole number up there. Let's just do a small number. Oops, how do we get there? Let's say 101011. Well, to get this into a decimal equivalent, all I need to do is find out what the decimal weight of these powers of 2. So what's 2 to the 0? 1. What's 2 to the first? 2. What's 2 squared? 4. What's 2 to the third? 8. Well, what's nice about powers of 2s, you just double the previous one. 1, 2, 4, 8, 16, 32, 64, right? 128, 256, 256, 512, 1,024, 2,048, 4,096, 8,192, 16,384, 30. You can see I've dealt with binary a lot, right? But all you do is just take the one before it and do what? Just double it. Over here, this would be, then over this side, I would just put it over, so the fraction is the opposite of a whole number, right? You understand? So 2 to the -1 would be 1/2. This would be 1/4. This would be 1/8, 1/16, 1/32, and that's the way we would do that. Up here, this would be 1/10, right? You understand, right? And then what I can do is I can just add all these weights together, and that would give me the decimal equivalent of this number. Let's don't do the fractions right now. So what would be the weight of it? What would be the weight of the number? Well, all I have to do is add 32 plus 8 plus 3. And what did we come up with? What's that? 43. and this is base 10. And now I've got a feeling of the weight of the number, because now I've got it in decimal. So this would be a binary number. We've got two types. We got what they call a digital sensor. A digital sensor has a single bit analog to digital converter. So what we do on that is we take a special integrated circuit called a comparator. And then what we do is we bring our unknown into one side. And then I come up here, and we'll have to power this thing up. I need to redo this a little bit because I need to draw it. Now, if it's adjustable, it's going to look something like this. And I bring this into the other input of my comparator. And this right here would be adjustable. So if I set this at 3 volts, then what happens if this input comes up here, no matter what it's doing, as soon as it exceeds 3 volts, then the output would go true, whatever true is. Let's say it goes to 1. So these guys are going to have to be powered up, right? Does that make sense? And then when it comes down here and drops below 3 volts, then the output should drop to a digital 0, or whatever that is. Now that's going to be a voltage level, right? You understand that? These devices are called comparators. They've been around for years. And a lot of times this will be built into the sensor. So the sensor will have a sensing element out here. Whatever it's sensing is an analog sensor, and it'll be built into the sensor. And then it's got an output. So it's going to have a common, right? It's going to have a power lead, and then it's going to have an output lead. And these are what we call 3-wire sensors. So if you ever see a sensor that's got 3 wires on it, then it's some type of solid state sensor or electronic sensor, right? You understand that? And a lot of times we'll have a little set screw on it where you can adjust what we call the threshold, where it switches from what? A true to a false. And that's an A to D converter. So I'm putting, but it's a single bit A to D converter, right? You understand? So what am I putting in? I'm putting what? Analog into it, but it's coming back and giving me a true false out. But if I'm measuring temperature, a true false on a temperature might be okay. You know, I can say, okay, when I get up to a certain temperature, I want to cut my fan on. When I drop below that temperature, I want to cut it off. But a lot of your computers now, except laptops, those dang fans run at a different speed depending on the what? Temperature. Well, now we've got to take an analog sensor and get it into a binary number that the computer understands. That makes sense? So most AD converters is going to give us multiple bits output. We'll look at that in a minute. But what's nice about this is using voltage, easier to process with a digital computer. Easier to transmit because now we're not dealing with a voltage level. We're going to be dealing with a level that's going to be true over a range. I think I told you about a digital method called TTL. Some people call it this. It stands for transistor logic. This guy will accept anything above 2 volts, between 2 volts and 5 volts. It will accept that as a legal 1. So I don't have to get 5 volts to it. I can get anything between what? 2 and 5. And it would be considered a legal 1. Down on my low side is 800 millivolts down to, I think it's minus 700 millivolts. It would recognize this as a legal 0. So now I can live with a little bit of ground shift, right? You understand that? And we have other methods where we can live with more. There's a method called RS-232, which accepts anything from a minus 3 volts all the way up to a minus 17 volts. It accepts this as a logic 1. And anything between a plus 3 and a plus 17, it accepts it as a logic 0. So this was kind of strange when I got into this, because usually the negative, you think that's going to be the 0, but for some reason RS-232, they chose the negative to equal to 1. So now, good gracious, I can run this thing off of almost anything and send it long distances. They guaranteed it. The specification said 50 feet, but I saw this stuff. The higher the voltage level you have, the further you can send it. Standard was around 15 volts, because that way you could shift. So 15 volts, think how much that sucker could shift before it got below 0 volts, right? You understand that? Which was really neat. I seen RS-232 run thousands of feet. And you didn't have to worry about the ground shift, because why? Because you had such a big range. So if you shift 1 volt this way and you're using 15 volts, your receiver would see it as a -14 and a plus 16, which is still what? This wasn't 17, guys. This was 25. It was a plus 25. Plus and minus 12 was the most popular use. In fact, when the IBM PC first came out, that was several power supplies, and plus and minus 12 was available for the RS-232 port.
The RS-232 different from the old RS-232 serial cable we use.
There's no such thing as an RS-232, which is a received SIN. It's an IEEE standard. Well, actually, it was an ETA standard.
We're using on the Golden computer block.
Yeah, that was ORS-230. I don't know why they called it an ORS-232.
It's always serial cable.
It is serial. It's a serial technique. Serial is one of the main methods that we use to transmit information. And what advantage does serial have over parallel? I understand serial. When we send digital information, what's the advantage of serial over parallel? So right now I'm sending you information. Am I sending it parallel or am I sending it serial? I'm sending it serial.
Oh, down there on the crystal line, those are serial cables. Oh, those RS-232.
No, those are on the Amatro line. The Amatro line is using something called Profibus, which is a serial. The big advantage of sending digital information serially is it takes a lot less wires. Copper costs a lot of money. Copper is a lot of money. And if I was trying to send digital information and I was trying to send it, so now we're dealing with the packets for the internet is like 1,024 bytes. So that's a lot of data. And if we're sending it parallel, we would have to have at least one wire for every bit that we send. We send digital information to our TVs now. Used to, video was analog. And now, what are they sending through that cable? They're sending digital. How many cables do you have coming into the back of your TV? One. So serial is a lot cheaper. It's not as fast as parallel, but it's so much cheaper that it has a lot of value. But so digital is easier to process by the computer. It's easier to transmit. I can store. So now I can store this in little batteries, because we're not concerned with a precise level as long as we can go back. So on your car, as long as you recharge the battery before it goes dead, the battery will stay charged, right? You understand that? That makes sense. So every time you crank your car, it uses a lot of the potential in your battery. Your battery voltage drops down, but as soon as your car cranks, what does it do? It starts charging. So we use a type of memory in our computer. Predominant memory in the computer is called a dynamic memory, and it's nothing but these little tiny capacitors. And those suckers, they're nothing but batteries. So as soon as you store something in there, what do they start doing instantly? Discharging. So what do? We constantly go back and recharge them. Computers, they technically call it refreshing. This is called dynamic memory. And it's been around so long that the refresh is done automatically. You're used to your programs had to go back and just rewrite everything into the memory, but they've got hardware now that comes back and refreshes your memory. So it's a predominant memory inside computers. Easier to store. So what's nice about storing things is we don't have to use it instantly, right? We can store it now and use it later. We can store it now and compare it to things later, right? You understand that? See if they're the same. The resolution. What is a resolution? Anybody know what the definition of resolution is? I've heard that before, but if you don't know what it means, it don't mean it. That is the resolution, but what does the resolution mean? So when you change the number of pixels on your display, you're changing the resolution, but if you don't understand what resolution is, then changing the pixels don't mean anything. So when you
1024 by 768.
Yeah, but what does that mean? I mean, what does a resolution mean?
The clarity of your
Or the preciseness. We can't say that it's the preciseness or how precise something is, right? You understand? So right now, if I'm using a single bit, then I have very poor resolution because it's only going to recognize one voltage, right? When it exceeds that voltage, it's going to recognize it. When it don't exceed it, then it's not going to recognize it. It's not going to be true. But if I'm trying to figure out what temperature it is, I cannot use on and off. I've got to have what? I got to have a weighted binary number that indicates what? The temperature. I've got to have a transfer function. So what we do in binary, the more bits we use to represent the analog value, the higher the resolution. So if I'm using 4 bits, then I can only have, and I'm using voltage, I can only have 15 voltage levels. I can only represent 15 voltage levels. Because with 4 bits, I get 16 combinations. But one of those combinations is 0, and 0 represents a no voltage, right? So when we say, okay, so that means, but if I come up here and add another bit, then I go from 16, I go to 32 or 31. So I've increased the resolution of what I'm representing, right? Y'all understand? Y'all follow this? So let's say I'm using an A to D converter that's only 4 bits. And then I'm going to take 15 volts. My sensor is temperature, and it gives me a maximum of 15 volts. And then my transfer function, I have 15 steps. That means I'm going to have 1 volt per step. Okay. So that means if I put in 1 volt, I'll get that. If my sensor gives me 2 volts, I get that. If my sensor gives me 2.1 volt, I can't represent that, right? You understand that? If my sensor gives me 18 volts, I can't represent that, right? I've exceeded the range. So here our resolution would be 1 volt. That would be the resolution. So we couldn't do fractions. We couldn't do a lot of things. So the more bits I add to my binary, to my analog to digital converter, the better resolution is. That makes sense? Yes or no? So a lot of the A to D converters that we have inside, so a lot of PLCs dealing with an analog world, we got to understand that predominantly our world is analog, and our computers are what? Digital. So we had to come up with a method of taking analog and converting it into a weighted binary number, and these devices are called analog to digital converters. AECs. These guys have been around for a long time. These guys are, we deal with such an analog world that a lot of your programmable controllers, and these are computers that are designed to run machines, most of them now come at least with 1 analog input. But when they come in, they're going to run into an analog to digital converter, And then that analog to digital converter is going to take that analog value and somehow convert it over to a binary number. The 1100s that we deal with, they use 10-bit analog to converters in there. Now I can calculate the number of combinations by taking the base I'm dealing with, which is base 2, and then I can raise that base to the power of the number of bits that we're using. So if it's a 10-bit analog converter, this would give me the number of numerical combinations, which would be 1024. So I can take my input now and split it into 1023 different numbers. That makes sense. You okay, Melvin? You over? Now, why can't I do 1024? Because one of them's 0. So this is a real popular A to D converter. But now, if I'm getting 10 volts out of my unit, and I'm splitting that into 1023 combinations, and we call these steps, then how many digital steps would I have? Anybody got their calculator? What would be the transfer function? I'm sorry. We can say we'll probably go a little further than that. Like 9.7 millivolts, right? Per count. So now my resolution goes way up, right? You understand that? So now I can represent temperatures. We still can't deal with infinity because this is the problem we have with digital is I'm going to have to give up on my bits sooner or later. I can't have an infinite number of bits to represent. So every A to D converter I know of will have a resolution. And it all depends on the number of binary combinations it gives you for whatever whatever analog value you put in. In the industry, by the way, this is pretty standard, 10 volts maximum. That's for the input on the AD. Now, they'll usually accept some things over 10 volts, of course, because it's not going to blow up on you. It's just that if you put over 10 volts in on it, it's not going to give you a true value. And if you put under 9.7 millivolts on there, it's not going to give you a true value because now you're out of the resolution of the A to D converter, right? You understand? And basically they're going to kind of round on you. So if you come up with like 8.3 volts and it don't fall on an exact count, then it's going to give you a whole binary number that represents that weight. It's not going to give you a binary fraction. I don't know of any A to D converters that give you a binary fraction. It's going to give you a whole number, right? You understand that? That makes sense. We got several analog sensors on our manufacturing line. Toward the end of the semester, we'll go back over there and look at them after they make more sense, after we've done some labs and stuff like that. So we'll probably finish the class up over there. So A to D converters, it depends on what time they are. We bring analog in, then we're going to take the analog and some PLCs come with analog output ports. So analog output ports are not going to give you an exact voltage. It's going to take that voltage and represent it in steps. You understand what I'm saying? Because what we're going to do is we're going to take a binary number and we're going to put it into our DAC. What's a DAC? Yeah. And when I put a binary number on that DAC, if it's a 10-bit DAC, then it's going to give us 1023 steps. But the analog digital output is going to move in what? It's going to move in steps. So if I was to see a sine wave, the sine wave like that looks like that. But I think I showed you on our digital scope over there, and it was actually in what? It was actually in steps. And this is straight up. I'm doing it at an angle. And that scope is a digital analog converter. The more we sample, the faster we sample. So your analog to digital converters, some of them have what they call a sample rate. The faster you sample, the more accurately you're going to be able to represent the binary number, right? The analog value. So the faster I send these out, the slower these slopes, the closer these slopes get together, and eventually it's going to appear like this. Or we can filter it. We can run this through filters like inductors, and we can take a crummy digital output and turn it into a pretty nice analog signal, like variable speed controls for variable frequency controls. I don't like calling frequency controls. And for AC motors, variable frequency control. Yeah. These guys output a real choppy signal, but they filter it before it actually hits the motor. Some of them do. Sensors, the most common output of sensors is what? In controls, they can be AC. If they're DC, they're usually on the range of 24 volts. AC, they can do just about anything. Current, the nice thing about current is that current is less susceptible to what? Electromagnetic interference. So we have several standard current values out there. The 4 to 20 milliamp current movement. Now, normally, if the sensor does give us a resistance, we're going to do what? We'll convert it to a voltage or a current, usually in the sensor itself. The current, of course, is the easiest to do. Voltage, is the easiest to do. And I think we looked at this. So all I got to do is to take a sensor that changes its resistance. All I got to do is put it in series with a fixed resistor. That's all I got to do. So if I came over here and took that sensor and did it like this, right? You understand? Then what we would be doing is we'd be changing a current, but we wouldn't be changing the voltage. You understand that? Yes or no? If I put a fixed resistor in series with it, then when this guy here changes its current, then what's going to happen? It's going to cause this guy to drop what? A voltage. And then now this guy's going to drop a voltage. And then Kirchhoff's voltage law says what? The sums of those two voltages have to equal to the applied voltage. So if I come over and take my output right there, then what am I going to get? Well, I'm going to get a varying voltage that varies with whatever the resistive sensor is trying to measure. And then I can either use that or bring it into an A to D converter and convert it to digital and use it with a computer. And our predominant controls guys now are computers. We call them what? Yeah, programmable logic controllers. PLCs. So just about any place you go now, you're going to run into PLCs. Because the information it's bringing in, we can transfer it over great distances with little trouble. We can bring it in, we can process it, we can store it, we can share it between other PLCs on our network. So it's really, really neat. So even in current, the current interfaces, eventually you can convert it over to. So voltages, AC, we use a device called a triac, which is solid state. It's really, really neat. And the symbol for a triac is this guy right here. And then we have a lead called a gate. And then I can't remember. One of them's called MT1 and one of them's called MT2, but I can't remember which one it is. And this guy's basically an electronic switch. So I come up here and put some type of pulse on this gate, and this guy turns off. I take the pulse away, it does what? Turns off. But this is solid state. This is solid state. We use these all the time. So if you got motion detectors on your house, how does it turn that light on and off? Turns it off and on with a triac. Guarantee. In fact, I had one go out one time and fixed it.
I got one out right there.
You can take it apart. It's probably got two devices in there. It's got the light sensor, and then it's got the motion detector. And then it's usually got another device in here called a DIAC, and we're not going to get into that. But, and then this will go to your sensor. A relay. Now, what advantage does solid state have over relays? What are relays? I've all had motor controls. What are relays? These are electromechanical devices, right? And anytime your car is an electromechanical device, which means what? It can fail mechanically or it can fail what? Electrically. Another problem we have is that relays take time to switch from off to on. Solid state devices take time to switch between off to on, but relays, we're talking, milliseconds. Solid state devices, we're probably talking nanoseconds. So that means as far as how fast we can switch solid state relays, we're limited to how fast we can switch those things. Now, as far as turning lights on and turning lights off, we have no problem. But some of the things that we run into in controls, we cannot do them with PLC that's got relay outputs. Call a pulse train output, PTO outputs. These generate a high frequency digital pulse output. Pulse width modulation, these guys usually run about 15, 16 kilohertz. You cannot do pulse width modulation with a PLC that's got a relay output. So these guys are going to have what? They're going to have solid state output. You wouldn't use AC on a pulse width modulation, by the way, but you might use it on a PTO. DC, we're going to deal with a relay. Now, what's nice about a PLC that's got a relay output is that it don't care if it's AC and it don't care if it's DC. It's gonna give you a real wide range of voltages too. So we could use 28 volts AC. Most of them give you the ability to use 120 volts AC. I've seen them go up to 240 volts AC on the PLC output. DC would be about the same on DC. So what's nice about a relay is you're not dedicated to the amount of voltage you put on that thing. The triac, The triac has what we call a breakover voltage. When you turn these things off, there is a path that you can get through. And if you exceed the breakover voltage on a triac, it will break over and it will be bad. That's not good. So relay outputs have the advantage of what? Yeah, they're usually not dedicated to a voltage. I mean, we can put DC on, we can put AC on. We've got some solid state limit switches that they don't care if it's AC or DC because they use what? They use relay output. Now, when we get into DC, we're either going to use relay or we're going to use what we call an NPN transistor. Now, if you take solid state, you'll learn that. But we'll look at it later on. We got two ways. When we deal with DC, we got two polarities. What's our two polarities? Positive and negative. Well, an NPN sensor is designed to give you a negative when it's true, when what it senses is true. A PNP is going to give you a what? Positive when it's true. An SCR it'll give you, I don't know what it'll give you. These are the predominants we've got here. We either have a what? Relay, or we have an NPN or a PNP. Now this only comes into play when you're dealing with what? DC. And why is that? Because AC technically has no polarity. Why is that? It's constantly changing. I mean, it's constantly changing. This Alabama Power is changing polarities every 8.3 milliseconds. 8.3. So it has no polarity. It has no, so when we talk about a common on AC, it's not the negative, it's just a what? It's just a common that we make the measurement relative to. So when we get into DC, we gotta worry about the polarity. So if I'm looking for a minus when it's true, then I'm gonna use a what? An NPN sensor. I know my lines got together up there, guys, I'm sorry. And you don't really have to understand how they work. So an NPN sensor is set up for a positive common. A PNP is set up for a negative common because it's going to give us a plus, right? And a plus is looking for a minus, and a minus would be looking for a plus. Does that make sense? And then we also have current loop. This is DC. The most popular is 4 to 20 milliamp current. So electromagnetic interference, it's almost impossible for an EMI to generate a current. It's really easy to generate a voltage, but it's impossible to generate a current. This is why the 4 to 20 milliamp current loop is still very popular in the industry, because it's basically immune to electromagnetic interference. And also, over a range, it's really, really neat. It's basically immune to the resistance of the wire. Because what it does is it uses what we call a constant current source. A constant current source would have, so let's say a constant current source can put out 20 volts. Well, if it requires 4 volts to put 20 milliamps through that conductor and 20 milliamps through that conductor, you got okay. But let's say you lose 4 volts down the line. Well, that if you try to lose 4 volts because of the resistance of the wire, it'll cause the current to try to go down. But what's going to happen is the output of your constant current source will raise the voltage to cause what? 4 milliamps to flow. So what's nice about the current loop is it's basically immune to the resistance of the wire. It'll keep raising that voltage up until it runs out of voltage, and then you're screwed. And most of them have a really good range. So you see these 20 milliamp current loops run thousands of feet. Thousands of feet. So this is, in DC sensors, we have 2 types. We have what we call sinking and forcing. And so what we're doing, and the best way I can put it up is draw it like a motor control circuit. So on one side, we got our sensor. And the other side will be the input of it would be our load. Now, what is a common? So I'm going to come up here, I'm going to start connecting these things up, and all my sensors are going to be on the left, and the inputs to my PLC or my load will be on the right. And what's a common? A common is just a common connection spot for multiple devices. So the one on the left, this would be its common. The one on the right, this would be its common. Now what's on the left, the positive or the negative? Whatever you want. And that's where we get into syncing and sourcing. So if I come over here and put this plus, and this is minus, then this guy right here is running a positive common. That makes sense. This guy over here is looking at a what? A negative common. That makes sense. Okay. So that would be this guy right here. So a sourcing sensor, this would be representing the sensor. It's going to run a what? Positive common. Huh? Well, I'm drawing it in green. Yeah, I know it's time for that, guys. So this would be, I'm sorry, this would be my sensor, representing a digital sensor, right? You understand that? So usually when we use the term digital sensor, we're talking about a sensor that's going to either be on or off. Everybody understand that? Now, an analog to digital converter is a device that's going to take an analog input and convert it over to an equivalent binary number that represents the weight of that analog input. So what we're saying is that this would be an example of this guy right here. So it's using a what? A positive common. So these sensors right here would all be what? Sourcing. Now, if my sensor is sourcing, then my load is going to have to be sinking. You understand? So a sourcing sensor has to hook up to a sinking input, right? You understand that? Everybody okay? Yes or no? So if I come up here and change the polarity, then I'm going to be, my sensor see a negative common, and my load is going to see a positive common. Then these guys right here are going to be what? Now over here I'm using a what? I'm over here, I'm using a negative common, and it's hard to see because they're using the same picture, but notice what they're doing is they're changing the common, right? You understand that? So here my sensors are going to be what? We call these sinking sensors. And then my load is going to be what? Sourcing. Now some controllers give you the ability to establish the common. A lot of PLCs, this is set for you. The predominant method is the PLC's inputs are syncing. So if the PLC inputs are syncing, then I would buy sourcing sensors. Now what's a sourcing sensor? Yeah, sourcing sensor would be a PLC. The problem is that when you look it up, they don't say sourcing and syncing. They say it's an NPN sensor or a PNP sensor. So it's up to you to know the difference between an NPN sensor and a PNP sensor. So a PNP sensor is a sourcing sensor. An NPN sensor is a syncing sensor. Whether you understand about NPN transistors and PNP transistors, it don't really make any difference in this class. If you take the solid state class, which is not part of the AUT, but if you're ILT, solid state is one of your core classes. You'll learn about NPN and PNP transistors. All we need to know in this class is which type of DC sensor do you have. Everybody okay? Yes or no? Okay, y'all take a 2-minute break, guys. What time does this class get on? 12:30. So everybody okay on syncing and sourcing sensors? These are digital sensors. These are going to give us, so notice in each one of these applications, they're talking about these things here acting like a push button switch, and that's what they are. A digital sensor acts like a switch. So it either gives you a true or it gives you a false. What we're doing is changing what's a true and what's a false. So one of them gives you a positive for a true, the other one gives you a negative for a true. Everybody understand that? Yes or no? All the sensors that we're going to do in this class, and it's not exactly true, are going to be AC sensors. So in this class, we're going to do motor controls. That's why you got to have motor controls first. So all these sensors that we're going to see from our point of view are going to be AC sensors. Are the sensors themselves all AC? No. We have our temperature sensor that we're using is a DC sensor. Now we'll look it up and see what we got the data sheet on it. I don't know if it's syncing or sourcing. But what they do on that guy, I don't remember what it is they bring it out and use it to energize a relay. And then the contact to the relay is going to give us 120 volts AC. So this is on the actual module itself. This is not inside the PLC. So the pressure sensor that we're going to use and the temperature sensor we're going to use, these are both DC sensors. So we're going to have a DC power supply that we plug into the wall to power these suckers up, right? Does that make sense? And then they're gonna, then they're gonna control a relay, and then we'll have 120 volts across the area. Let me pause this and let me go get that just over there. Let me bring up my, so this is one of our sensors, and this is the DC sensor. So whether it's syncing or sourcing, I don't know. Whether it's a PNP or an EPN. One of the sensors we got actually has a PNP on it, I think. It's highly likely that this is a PNP sensor. But they don't say it on the sensor itself. It always looks better when they're in photo. So this is our sensor right here. This is a temperature sensor. That we'll get to. And so here's the sensor. Here's the leads that come from the sensor. Then it's got this guy right here. This is where you plug in the DC power supply. And these are relays. It's going to be a plug-in. It's going to be like one you charge your phone with, stuff like that. A little plug-in power supply that you plug into a power strip. You understand? Well, they're DC. They step down and then they convert it to DC. And since we're using relays, guys, we'll talk about this. We need to understand this too. Since we got relays, we're going to have something to see the diodes, the discharge of relays. So these are the temperature sensors, and the pressure sensors we also have. Those are DCs. But when we specify for our motor control trainers are 120 volt trainers. So they built these up for us. By the way, the color code is standardized too if it's a 3-wire sensor. So we have 3-wire sensors and we have 4-wire sensors. Most solid state sensors has one contact in it. So if you need multiple contacts, you'll have to use a solid state sensor to pick up a control relay that's got multiple contacts. PLCs is no big deal. You can bring in one contact, and inside a PLC program, you can use that contact as many times as you want to. So you can make a single contact sensor appear to have thousands of contacts if you need to, right? You understand? A 4-wire sensor is a single pole double throw sensor. You know, understand single pole double throw? Everybody okay there? The types of switches that we have. Everybody okay? Anybody need to go over that? Well, we have different types of switches. And most of y'all are familiar with this one. So the number of switches you have, we call it the number of poles. So this would be a single pole, single throw switch. This is what we use for our light switches and everything. Then we come over here, we bring in one switch, and then we give that switch 2 different conditions. This is a single pole, double throw. So some of our sensors are single pole, double throw, and we call them 4-wire sensors. Now look at the color code. So your power, if it's 24 volt sensor, which they predominantly are, your power is going to be brown. Your minus is going to be what? Blue. And your signal is going to be black. And this is squeeze people up because over here in the USA, we want to use what? Black for ground. And on solid state sensors, guys, that's wrong. The black is your signal. These are your single pole, single throw. These are your 3-wire sensors, so they're using a single pole, single throw output. Whether it's solid state, that's what we see. It acts like a single pole, single throw. A 4-wire sensor is a single pole, double throw. So we still have brown for what? Positive, blue for negative, signal is what? Black. And your other signal wire is white. So that's standard. So if you ever see a 4-wire sensor, a DC sensor, you're going to have brown, blue, black, and white. That's solid state. Yeah, these are either going to be your PNP or your impedance sensor. This, I don't know where I got this off. This is off the internet somewhere. This was really neat. We showed a 3-wire sensor. A 2-wire sensor is going to be black and brown, I think. And it's going to power up through the circuit itself. But we do have some solid state sensors that don't have to be externally powered. They power up through the circuit themselves. Resistance, voltage, a simple voltage divider, we looked at that. So voltage divider, we can have a 2 resistor voltage divider. And these are for sensors that vary their resistance. So we can take a fixed resistor and then we can put it in series with our sensor, which I'm going to draw as a rheostat, because that's basically what right? You understand that? And then I'll put plus up here right now. And then I can take my output right here, or you can reverse it and you can put your sensor up here, and you can take your output. Your sensor would be right here and your output would be right there. So now my sensor is going to give me a what? It's going to give me a voltage that's going to be proportional to, depending on the resolution and the accuracy. Now when we figure transfer functions, guys, we're figuring it exactly, right? You understand that? Hopefully you understand that just about every sensor has an accuracy measurement. It's going to be a plus and minus type thing, like plus or minus 1 degree or something like that for a temperature sensor. But we can't deal with that. All we can deal with is when we calculate our transfer function is to say this is what we should get, but in actuality it might be what? Slightly different. So this is 2 ways we can take a resistance and convert it into a what? A voltage. And this is the predominant method that we use to generate a voltage. It's not very hard to do. Now this guy over here is going to have extremely high resistance. I mean extremely high. Or we end up with what we call a loading effect, right? You understand that? What do I mean by a loading effect? Now let's say I have this hooked up to 100 ohms, and this is 100 ohms. That's 5 volts. Then right now I would have 5 volts. Everybody understand that? But what if I come over here and hook this up to a 100 ohm resistor? Well, this is not seen as 100 ohms, even though that's what my sensor's giving me. It's seen as 50 ohms. So my output voltage is now wrong. Right, you understand, because of the loading effect. But if I came over here and made this 10 megohms, and that was 100 ohms, then the loading effect would be so small it would be what? Negligible. When we deal with these voltage dividers, we're going to have to deal with what we call a loading effect, which means the actual voltage you get up, it depends on what you put it into. Now, your PLCs and stuff like that will have extremely high input impedances, and this is why they're susceptible to noise. Because the higher the impedance is of the circuit, the more susceptible it is to electromagnetic interference. And people think you can take an voltmeter, and put it into a circuit and not affect the circuit. Is that true? That is false. Your meter is like this. Your meter is nothing. When you put your meter across a circuit, it is acting like a resistor in parallel. So one of the measurements you got to understand is what's the input resistance of your meter, and that's going to be one of your specifications. Most of your digital meters are around 10 megohms. But we got a circuit over, and we'll look at if you take solid state. where we have to consider the resistance of the meter. So as long as I'm measuring 50 ohms or 1K or 10K, and I'm putting that in parallel with, I'm putting a 10K in parallel with a 10 mega ohms, you calculate the resistance, it's going to be 9.9999 ohms, right? You understand? It's all practical purposes. But if I come over here and this is 10 mega ohms, and this right here is 10 mega ohms, then I'm not, then my circuit, I just screwed, I changed my circuit. Back when we had, a long time ago, before we got digital meters, we had Simpson 260s, and those were pretty good. But their input impedance varied with what range you put it on when you was measuring voltage. And we had one of our guys there, we had a high impedance mag amp. It was a magnetic amplifier. This is before we had all the amplifiers we had now. And this guy went into number 4 galvanized line, and he wanted to measure the output of the mag amp. And the mag amp was sensing too much current, too much everything. So it was a safety device trying to sense if the motor was pulling too much current. He put his meter in parallel with that mag amp, and what did he do? He shut number 4 galvanizing line down just by taking his voltmeter and putting it across a high impedance circuit. He halved the resistance. The mag out put out the wrong voltage, and he shut number 4 galvanizing line down. Anybody ever worked at number 4 galvanizing line? Number 4 galvanizing line had a relay panel, and then it had a door back here, and you could get back in here. And Dennis was back in here, and all the foremen come running there to try to figure out what happened, and Dennis stayed inside that door, and they never knew he was in there. So they come in there, and they was talking about what went wrong, and the motor overcurrent and all this kind of stuff. And Dennis just stayed back there in that little cubby. And they reset it and come back on. We called them blue hats, and all the blue hats come running there. The dentist came around. Then we tried to figure out what he had done.
Did they get him severed?
No, he never knew it, but he did tell the story. So yeah, it was funny.
So is that circuit you drove called the Wheatstone?
No, this is not a Wheatstone bridge. This is a voltage box.
Okay.
The problem with the Wheatstone bridge, the problem we have with some sensors is we need to establish what zero means. And here I can't establish what zero means. The problem with a sensor that varies its resistance is it will never have zero. So if that sensor so when it's trying to say I'm measuring 32 degrees, or if I'm measuring 0 degrees Fahrenheit, it's going to output a voltage, right? You understand that? So what I got to do is come up and establish what a zero is, and then other advantages of using something that we call a Wheatstone bridge. Now, Wheatstone bridges, normally when they draw them squirrely. So normally when they draw them, they try to draw them in the shape of a diamond. I don't like to do that. I like to draw them like this because they're easy to understand. And what we're going to do is we're going to take our output. So let's call this common. And then we'll come up here and we'll put plus 10 volts right here. But what we're going to do is we're going to take our output right here. So what I'm going to do right now is I'm just going to put a voltmeter right here. Now this is going to be an analog output. So let's say this is 1K, this is 1K, this is 1K, this is 1K. What would my meter in the center measure? This is the kind of questions they give on the sequence test, by the way. What would my meter in the center measure? So what would we have right here? We know the resistors are the same size. If they're the same size, they drop the same voltage. We've only got 10 volts applied. So that means this guy would drop 5 volts, this guy would drop 5 volts. So relative to the center here I'd have plus 5 volts, here I'd have plus 5 volts. And what would my meter measure? My meter would measure 0. There's some people that says 10 volts, but it don't. It measures, your meter measures a difference of potential. So even though these two devices are dropping voltages, that meter, it sees 0. You understand that? So what if I came over here and this was my sensor? And my sensor could vary anywhere from 5, so it put out 500 ohms, right? And then it came up here and went up to 2,500 ohms, the maximum. Well, what I could do is I could come over here, and now it's the ratio of the resistors, guys. It's not, the resistors don't have to be the same size. So I could come over here and I could come over here and I could use a 10K and a 1K, and over here I can use a 10K. Over here I could use 100K and a 10K. I'm trying to get this. I'm running out of space. Now, what's the ratio of these resistors? What's the ratio of these resistors? They're the same. So what would I measure over here? I measure 0 volts. Yeah, if the ratio, and they have to be, usually we take the top one and divide it by the bottom. So it's 10 to 1. Well, the one on the other side is 10 to 1. It has exactly the same ratio. So that means these two resistors are going to drop the same voltage. This guy here is going to drop 1/11 of the voltage. This guy over here is going to drop 1/11 of the voltage. If both of them drop the same voltage, then I'm going to measure 0 there. So what we're looking at on the Wheatstone bridge is not that the resistors match. It's the ratio of the resistors have to match. Y'all understand over here? So I could leave this as a 1K, and I could leave this as a 1K. Well, I could change this to a 10K on this side, right? Well, what I would have to do on this side, if I adjusted this up to 5K, then we would say the bridge would be balanced. Because across the center, if the ratio is the same, the bridge is balanced. If the bridge is balanced, I get 0 volts across the center there, which is going to be the output of the bridge. So the output of the bridge is going to be the center. That's where I'm going to send to my A to D converter, the output of the bridge. But what I can do now is I can come over here and do what? This over here might be a 10K. This right here might be a 10K. I have no idea what that is, right? You understand? But I know I've got it in a glass of ice water, and it's a temperature sensor, and it should be measuring 32 degrees, right? You understand that? So I could calculate my transfer function, and I would adjust this. So I'd say my maximum I would get out would be something. We'd figure that out when it was down at this minimum. I'd figure that out, and then I would get my transfer function, and then I could come up here and adjust this. Well, I wouldn't even need that. I would just start adjusting that. So I've got it in ice water, right? You understand? I don't even know what the minimum output of my thing is. I'll start adjusting it until it measures 0. Right? And we'll probably do it in centigrade. Centigrade's it's a little harder to understand this in Fahrenheit. Why? Fahrenheit is a stupid scale. Why is it a stupid scale? Well, not only that, we freeze at 32 when we boil at what? 212. So this is easier to teach with Fahrenheit, because Fahrenheit we freeze at what? 0, and we boil at what? 100. Water boils at 100 at sea level. Now, you know that changes depending on whether you're above or below sea level. Because why does it change? Because of pressure varies. Pressure varies with amplitude. Pressure pushing down on the top is what's keeping it from boiling. So the lower the pressure, the faster it boils. That's why these people that did this mountain climbing, it's hard for them to get hot tea, because they're down below freezing and the water boils real fast. So sometimes they have a pressure thing that they put them in to make it boil at a higher temperature. So what I can do now is I can put this into a reference, right? You understand? So I can apply a reference pressure to it. I can do whatever and apply a reference to it, and then I can do what? I can establish what 0 means. And once I know what 0 means, then my transfer function means something. Well, that's what we can do with the Wheatstone Bridge. We can establish a constant value that we can reference it from. Or we can compensate for things. We'll look at what we call a load cell. These are devices that measure weight or measure force. And we have to compensate for temperature with us. We do it with a Wheatstone Bridge.
On the Wheatstone Bridge, is that, I don't know if I ever asked that. It's different last class. If they ask it, it's the Wheatstone Bridge balance.
You just take the top resistor and divide it by the bottom resistor.
I just had an epiphany.
If you come up with the same number, it is what? Balanced. If you come up with a different number, it's what? And what's nice about it is here we got centigrade. The problem is that what happens when this goes below is this right here. Well, what happens now is this will become positive. I'm sorry. Is that the polarity of the voltmeter will change. So if your voltmeter shows a negative voltage, it means it's below your reference. If it's a positive voltage, it means it's above your reference. So now I have the ability to measure negative and positive quantities with a Wheatstone Bridge. Can't do that with a voltage divider.
I don't think they ever drew it like that. I think the only one I ever saw.
Yeah, and it's hard to see when you do it like that. It's nothing but a series parallel circuit, and it's a very simple series parallel circuit. But if you look at it, and they'll come over here and they'll say, well, we're going to take that. Well, that's the circuit right there. So we got two here. We got two in series there. This is the circuit, and this is why I like to draw the Wheatstone Bridge like that. But it's got the name Wheatstone Bridge by the way we draw it. So anything that we draw that's kind of like a configuration like this, they call it a Wheatstone.
But it's the same thing.
It's exactly the same thing. But it's easier to see and it's easier to understand if we draw it.
So you just take the ratio.
The ratio, right. And you can figure out, so the low ratio would be your negative side, and if it wasn't balanced. Your low ratio would be the negative side, and your high ratio would be the positive side, so you can calculate polarity too. You understand? So if I got over here and this had a ratio of 5 and this had a ratio of 10, then this meter would measure negative. If this was my negative side of my meter, right? You understand? So if this ratio is lower than that one, then we get a negative voltage. If this is higher than that one, if this is higher than that one, we get a positive voltage. So it's real easy to see what we can do with the Wheatstone Bridge is not only can we set a zero reference, but we can also tell if it goes above that reference or if it goes what? Below.
Okay, so when you say that reference, what are you doing with the variable, with the sensor itself? I mean,
you put it in whatever you reference it to. If it's a pressure sensor, I might put it under 100 psi.
Okay, I see.
Or I might put it in a vacuum. 0 psi is really hard. We can actually, or put it in a vacuum, right? You understand? If we could put it in a vacuum, then that would give me a 0 psi reference.
So something that you know.
Yeah. So your Wheatstone Bridge, you're going to have to balance it or set a reference. Now with scales, we do that outside with a load cell, which is a device that measures weight. We set 0 outside, so we go out there and we'll take all the weight, because even on a scale, you always have weight on the scale, right? Yeah, we call it the bridge. Truck scales, we call them bridges, or whatever sets that you put your stuff on. We call that, on a truck scale, we used to call it a bridge, because that's what it looked like. The trucks would drive up on the bridge. And what we would do is we would come out and we didn't adjust it at the Wheatstone Bridge. We adjusted it at the indicator. What we would do is we'd put 0 weight on it, and then we'd go in and 0 our scale. And then we'd come up and we'd put a certain amount of weight on it, and we'd tell the digital analog converter that was the weight, right? Understand? And then we'd set what they call the span of the scale. But we use a Wheatstone, low cells use Wheatstone bridges because of another feature we'll look at. So load cells uses something called a strain gauge that varies its resistance with weight. And a load cell includes the Wheatstone bridge in the cell itself. And so what we do out of that is we get a voltage out of that represents what? That represents weight.
What's the smallest one you've ever seen? I've always seen truck scales, but on our line down here,
There's no scales
we
on
could
them.
put something on there where we would weigh those.
Oh yeah, I've seen counting scales that would actually count by weight. I mean, they would count almost feathers. We can make them things that count almost anything they were
So
so.
we can get very small.
Yeah. So we have scales, you know, we have counting scales all over the place. And a lot of companies use them for inventory. So instead of going out there and counting, Hager Hinge down there, we used to go out every year and provide them a lot of counting scales because they made hinges. And they made thousands of hinges, right? Instead of going out there and say them, you'd go out and get 100 of them, you'd throw it on that scale and say, this is 100. And the scale would calculate how many one of them would weigh. And then you go over, so neat, you take one hinge, you throw it on that scale, and they go one. So what they'd do is they'd take the box, they'd put it on there, they'd zero the box out, and they'd just start throwing hinges in there, and you'd count them. You know, so counting scales have been out a long time, but they're just nothing but weight. We had them that weighed a place in what was that, gang? They made syringes, little plastic syringes. They made the blades for scalpels too. And then we had counting scales. So they'd be coming off that thing. We just count them. But it counted them by what? By weight. So those things don't weigh hardly anything. So they're pretty accurate. This is a typical, so we okay here? Everybody okay? With a lot of things. So Wheatstone bridges, we use that when we have to establish a reference, right? You understand that. If we don't have to establish a reference, then a voltage divider would be fine. But both these, the voltage divider method or the Wheatstone bridge method is taking a what? It's taking a sensor whose resistance varies according to what it's measuring and converts that into a voltage which becomes usable now, right? You understand? Because we cannot transmit a resistance. Everybody understand that? So if we're going to send it, we're going to have to send it as a voltage, represented as a voltage or a current. If we're going to send an analog quantity. This is the basic setup of a control system. So we have inputs. We have something that's making our decision. This is where's the sensor going to reside? Now these are going to be inputs into our control. Everybody okay? And this is any control system. So there's my question I've already asked. In a control system, what are the things that may be needed to sense? And we've already looked at this, but these are some that we came up. We need to be able to what? Maybe need to sense position, speed, weight or forward, count. We gotta have some method of counting. Pressure, flow. We didn't bring that up. How fast fluids are moving, right? Temperature. We brought up that one. Light. We brought up that one. Thickness. How thick something is. We didn't bring that one. Time. Nobody brought up time. Gas levels. We did sense gases. Liquid levels, motion. We brought up that one. Orientation. We didn't bring up that one. Orientation would be. This is very important for robotics. Shape and size. Proximity. What's proximity? When it's by something, right? So a lot of people get position and proximity confused with each other. So position, we're trying to sense a target over a range. Proximity, we're trying to sense it when it's at someplace, right? When it's at a position. Everybody okay? Nobody brought that up. Moisture. You didn't bring that up. Viscosity. What's viscosity?
How thick?
how thick a liquid is, right? Color we brought up, which we didn't put on here. Any questions on that, guys? Everybody okay? And of course, this is just a list. I used to be in the habit where, when we brought up things that wasn't. Now we're going to talk about most of these sensors. The ones we're going to deal with are position sensors. We're going to look at speed sensors. We don't have any weight sensors. We do have pressure sensors. We don't have any counter. We don't have full system temperature. We have light. I think those are the ones, mainly the ones that we're going to be doing lab on. Let's see, proximity sensors. Level. We're going to be dealing with level sensors. The level's not in here. Oh yeah, it is. Liquid level. And of course, this sensor right here senses temperature. Now, this gives us the ability, and we'll talk about later on, we call it the span. Notice it's got two bands on it. And what we have the ability to do here is to set what we call a span. Y'all know what that probably means? The range of what's true and what's false. So some sensors will switch at the same level. This sensor right here, we can make it switch at, so we can make it switch, give us one indication when it gets above a certain temperature, and then we can give us another indication when it gets a lot lower. And y'all be making runs down to the cafeteria to get ice for that. Okay, guys, y'all take a 10-minute break.